So we're going to want to find summation notation to generalize all this. So for the right hand endpoint estimation for this particular function, we're summing up this expression. So k is the number of the subinterval I'm on times delta x. So in other words, if I'm on the 6th subinterval, my x value that I take to plug into my function for the height of that rectangle is going to be 6 times delta x. So I'm evaluating my function at k times delta x, and my function's x squared. So this is always going to be my height for the kth rectangle, and this is going to be the area of the k rectangle. Likewise, if I'm doing the left endpoints, my k rectangle is k minus 1. I'm taking it from the left endpoint, so it's k minus 1 delta x units from the origin is that value on my function. So that's my height. I can denote the height of the kth rectangle as k minus 1 times delta x squared. And then the area of that rectangle, I just multiply by the width, which is delta x. So notice that the only difference that we're getting when we're summing all these areas of rectangles between the right and the left endpoint estimation is at the last rectangle and the first rectangle. So all these other, since the left endpoint of one interval is equal to the right endpoint of the interval before it, all the area contribution you get from these interior intervals is the same. So only the rightmost and the leftmost give you a difference. So we can show that by starting our index different, one less for the left endpoint than the right endpoint estimation. So I can still use the same formula for area of each rectangle for this function. But for the right estimation, I'm starting at 1, and I'm ending at n units, n times delta x units. I'm ending up here at the right endpoint, whereas for my left endpoint, I'm starting at 0, and because I'm ending at n minus 1 times delta x units. So let's look at this function in particular, if it ever loads. So this is 100 rectangles, and you can see that it's kind of brought Desmos to its knees. It can't really draw those too well. This is 100 right-hand point estimate. And you can see that's getting closer to the actual area. So let's look at this function x squared. So I don't want to sit down and figure out 100 of these areas and add them all up. So what we're going to try to do is find a formula that we can use to simplify these things. So this is the summation notation for my right hand estimate. So notice that I can factor out the delta x factors because those aren't involved in the summation. So I have delta x squared times delta x. I'm going to factor that out, and I'm just left with this. So this is one of those formulas that I talked about at the beginning of the video. This is the sum of the square of the first n integers. So you can look in the appendix to see how those are derived, Appendix E in our text. But this sum is equal to this expression. So I can substitute for this sum, this expression, and then whatever number of rectangles I want to use, I evaluate this at n. So for n equals 100 rectangles, I get delta x is 1 over 100 because my interval is 1. And then r sub 100, I evaluate this expression at n equals 100, and I get this value. So we're saying that as n goes to infinity, if we look at the limit, this sum is going to approach the actual area. So again, let's look at what we got when we substituted that sum with this formula. So if we look at the limit as n goes to infinity of these right-hand endpoint estimates, so I substitute r sub n with this summation. I factor out the 1 over n cubed. That's because that was my delta x. So now I have this expression because I substituted this summation with this expression. So now if I take the limit of that as n goes to infinity, that's just a rational function, and that evaluates to 1/3. So that's how we know that the actual area is 1/3. And we can walk through the same type of thing with the left endpoint estimate with this sum. And notice that when k equals 0 to n minus 1, we need to just adjust the formula that we use because k equals 0 is contributing nothing, but we're just going to n minus 1. So we are going to substitute n minus 1 where we had n before. And again, it evaluates to a different function, but that limit still goes to 1/3. Okay, so this is the case for any function. So far we've just been looking at f of x equals x squared. But the things that apply to any function are you can approximate the areas with rectangles. The more rectangles you have, the better the approximation. And the limit as n goes to infinity of the areas of your rectangles approaches the area under your curve. So this is going to be the general case for a continuous function that you want to find the area under the graph between the function's graph and the x-axis. So notice that here I have a different interval on the x-axis. Here my function's going from 1 to 3. So before my function was going from 0 to 1. So when the left end point of your interval is 0, things are a little bit nicer. But all we really need to do is shift everything over. So if my interval is AB, then I take that interval to get and I chop it up into n units, right? So my delta x is b minus a over n. So in this case, I'm starting at a equals 1, not a equals 0. So my intervals are going to start at a, and each interval is just going to, I'm going to add a delta x quantity to. So my first interval is a to a plus delta x. My second interval is a plus delta x to a plus 2 delta x, etc. So for the right estimate, the height of each rectangle is going to be a plus k times delta x. And for the left one, it's going to be f of a plus k minus 1 times delta x, like we'd seen before. So we're just replacing x squared with f, and we're just generalizing here. So again, this is a generalized form of the right endpoint and left endpoint approximations.